I'll turn the recording on Zoom, and Huffan's also recording on his phone. So, good morning, everyone. Thank you very much for coming to my dissertation defense. It's a real privilege to defend in front of you. And so the title of my defense is Proximal Byzantine Agreement. And also, for those who don't know me, but everyone does, my name is Roy Shadmon. So before we get started, I want to quickly thank my advisor, Owen. Thank you for all your support. The committee, Peter and Mosa Nasani, thank you very much for your insightful feedback and for your support throughout the years. I also quickly want to thank Daniel Spencer, an early collaborator, the two UC Berkeley organizations who partially funded my research, my siblings Noah and Ori who are in this room, Sana, my fiance, and my parents. So the agenda of the talk is split into 5 sections. The first section, I'll talk about the problem and the characteristics of the problem that we're interested in solving. I'll then present some related work and how state-of-the-art protocols address the problems that we're interested in solving. I'll then go and talk about my research and how my research addresses those problems as well. And I'll also compare and contrast our approach versus existing art. I'll then talk about some evaluations of how we evaluated our protocol and also how it compares in certain evaluations comparing to state-of-the-art. And then I'll end the talk with some future work discussions and also where I think the next generation of applications that can utilize my research in. So, what are the problems that we're interested in solving? So consider a drone network application where we have a leader drone in blue and we have a set of non-faulty correct drones in gray. The goal of this application is for the non-faulty drones to track the leader drone's location, and they do this by producing non-faulty estimates of the leader drone's location. So in an ideal world, all the non-faulty drones will produce a consistent reading of the leader's location. And then they can use some sort of mechanism where they propagate these messages to form agreement and know exactly where that drone is. But in practice, sensors are noisy and they often lead to their measurements being non-matching. And so in that case, when the measurements are non-matching, this prevents you from being able to use quorum-based mechanisms to determine exactly what the right leader's location is. So if everyone produces a different output, it's impossible to really tell what the true sensing value is. Another challenge in this system is that there can be malicious drones that can send misleading estimates to the other drones, and their goal is to get those drones to maneuver away from the leader drone. So the way we solve this is we need some form of fault tolerance mechanism to accurately and reliably track the leader drone's location, despite all these problems I just presented. But one thing about this research is we're not just interested in drone networks. These problems apply to many real-world applications. And the general kinds of applications that we're interested in solving is environments where sensors are producing noisy measurements, as we're seeing here on this graph. One of the things that's really important is that many of these applications can be safety critical, so making the right decision is very important. And so we need some sort of fault tolerance mechanism to be able to resolve these faults. The way we're going to approach this is by utilizing redundancy. So we're going to utilize multiple measurements to try to make these estimations. But one of the things when we're adding redundancy into our system, we also assume that there can be an attacker in the system that is very strong and can do anything it wants by producing any kind of output to try to make the decisions go in its preferred way. So the goal of our application is to be able to utilize some sort of stochastic estimation, and this estimation will end up feeding into some reactive control decision that a bunch of processes will end up making in a consistent way. But one of the challenges when you have fault tolerance and noise and you want to tolerate Byzantine adversaries is that there is this fundamental tension between accuracy and precision. Accuracy is the problem where everyone ends up just making a decision that's relatively close to the correct value. So everyone maneuvering towards the correct leader's location. Precision, on the other hand, is everyone makes a consistent decision, but that decision is not necessarily an accurate one. So it's just replica processes making the same type of decision versus accuracy where processes make the correct decision but they might not be totally consistent with each other. So how do related and state-of-the-art work solve these problems? So the first kind of protocols that I'll go over is an approximate agreement protocol. And this protocol is called Byzantine vector consensus. And the way this protocol works is replicas iteratively exchange messages until they reach this epsilon agreement property within the non-faulty convex hull. And so what does this mean? So if we have a set of non-faulty points in blue, and we have a yellow dot which represents the true value that we're trying to estimate, then the protocol guarantees that the decision will lie within this non-faulty convex hull that's outlined. So what happens is every round, replicas will iteratively exchange messages, and they will continuously do so until they converge within epsilon of each other. So they all will become precise in agreement. Once they satisfy this property, then they make a decided point. So they make a final point estimate that everyone makes, and they all make this precise decision together. But one of the things that can happen is that this protocol doesn't necessarily consider where that decision is relative to this ideal point in yellow. So in fact, the ideal point can actually be outside the non-faulty convex hull, but Byzantine vector consensus and approximate agreement protocols in general do not provide any sort of guarantee on where that decision is relative to the true point that we don't know. On top of that, there can also be attackers in the system, and the attacker's goal is to still satisfy epsilon agreement. Convergence will still happen, assuming the conditions of the protocol are satisfied. But at the same time, the Byzantine adversaries can move this point further away from this ideal point while still resulting in a valid decision. So a decision inside this outline is still valid, but it's not necessarily always going to be accurate. And so this protocol essentially provides a convergence mechanism for precision. Everyone is going to make a precise decision, but that decision is not necessarily promised to be an accurate one, let alone the decision is only guaranteed to be inside this non-faulty convex hull. On top of that, the protocol has this assumption where it requires a minimum number of replicas to provide these guarantees. And that requirement is that you need a minimum of n equals d plus 2 times f plus 1 replicas, where d is the dimensionality of the output domain, and f is the number of faulty replicas you want to tolerate. And so in this case, d in this graph is 2, and f is 1, so you need a minimum of 5 points to tolerate up to 1 faulty point. But one thing to notice here is that this requirement of replicas per dimensionality is often unreasonable in real-world applications. So if we consider a world where we want 6 dimension vectors to tolerate one faulty component, we need at least 9 total processes in our system that are redundant. And then if we want to tolerate 2 faulty processes with 6 dimensions, we need a total of 17 total processes. So this scales pretty quickly and also increases the cost of actually having this system in a real-world setting. The second kind of algorithm is sensor fusion. And Marzullo's algorithm prioritizes less on precision but more on accuracy. And it works as the following in one dimension. So say we have non-faulty points I, j, and k. Each non-faulty point comes with an interval guarantee. And this interval is guaranteed to constrain the true output of all the non-faulty points. And so Marzullo says, well, if all the non-faulty points, if all their intervals contain the true point, then the intersection of all the non-faulty intervals must also contain the true points. And so Marzullo says, well, the intersection of all the non-faulty points is between A and B. And so his algorithm says, well, the true output must be between A and B. But now, what happens if we introduce an attacker into this kind of system? So let's say we have a malicious point F, and it also provides an interval guarantee. So now Marzullo's algorithm says, well, we're only promised to have n minus f total non-faulty points in intervals as well. And so the intersection of all n minus f intervals will contain or should contain this true point. But what happens here is that the adversary, we first have an interval between A and B, between the non-faulty points, but we also have another n minus f size intersection that the Byzantine adversary added between C and D. So now Marzullo's algorithm goes and says, well, the true point has to be between A and B or C and D. But now we have 2 disjoint intervals. And so how do we differentiate between the 2 intervals? Marzullo says, well, the conservative thing to do is actually just to say the true point is guaranteed to be within A and D. And one of the challenges here is that this is now increasing the interval space and also increasing the uncertainty region of where that true point may be now by adding just one malicious point to, or one malicious adversary to the system. But this protocol isn't limited to one dimension. It extends to higher dimensional vectors. And so Brooks-Iyengar extended this famously and said, well, every non-faulty point has a bounding box around it that captures this interval in each dimension. So if you have a bounding box around I, another bounding box around J, and another bounding box around point K, then Brooks-Iyengar says, well, the intersection of the non-faulty bounding boxes contains the true point. And so the intersection here is this black box that I've outlined. So now what happens is that any intersection region that is comprised of at least n-2f intervals can be manipulated by f adversaries to create a new n-f intersection region. And what I mean by that is that any of these red boxes an attacker can create a new point with a bounding box that encapsulates these new bounding boxes in red, and it can increase the n-f feasible region of where that true point can be. And so if the Byzantine adversary outputs f with a bounding box around f, then we have a new feasible region that's added by this adversary. And now we have to decide how do we pick a point within this region. And so Brooks-Iyengar said, well, we could take the weighted average or the center point or something like that. But nevertheless, we will still be promised that we're deciding a point within this region. But the adversary was able to increase the possible choices that we could have made, and as a result, increase our uncertainty. The second issue that is introduced is that there is a very strict assumption that the intervals of non-faulty points contains the true point. And so if this assumption was not satisfied, or if we received a set of intervals that doesn't have an intersection comprised of n-f total intervals, then all guarantees and all promises of making some accurate decision are thrown out the door. So there's a very strict assumption here that these intervals the non-faulty intervals contain the true output, and if they're not satisfied in practice, which is hard to do, then you have no accuracy promise, or it cannot even make a safe decision. So what I'm trying to get across here is that there's a fundamental tension between precision and accuracy. In approximate agreement protocols, the entire point of these protocols is to simply agree regardless of what they agree upon, as Leslie Lamport remarked in the Weak Byzantine Generals problem. The focus in approximate agreement is precision and for replicas to form consistency on some points. And they do that by providing guarantees that will eventually reach epsilon agreement based on the protocol we use on convergence. They also promise that the decision will be bounded within the non-faulty convex hole, but they don't promise anything about this true unknown point that we're trying to estimate, so the real estimate of that all these measurements that non-faulty points have made. And so as such, there's less consideration for accuracy. On the other side, there's interval-based sensor fusion, and they make this very strong assumption that the intersection of n-f intervals must contain the true point, which is again very strong. And they do this because they can provide an accuracy guarantee. We're always going to choose a point in some region that is promised to include the true points. And they do this with the assumption that the n-f intersections contains the true point, and this n-f intersection is also quantifying how inaccurate your decision may be. So any point within this intersection region is technically valid with these protocols. So the one challenge here is that if multiple processes receive different kind of intervals, so we saw in Brooks-Iyengar the point F, imagine if point F was in the lower side of the quadrant with a different kind of intersection, each non-faulty process could end up making a different decision based on the inputs it receives, and thus there would be less precision, so they could each make a different but still safe decision. So how does my research address these problems? And so the biggest distinction is that we're modeling outputs stochastically. So we're throwing away all the interval-based assumptions, and outputs are modeled from a stochastic distribution. And specifically what I mean by this is that non-faulty outputs are sampled from a random variable, where the expected mean of this random variable is the ideal point we're trying to estimate. And so if at the bottom here we have a random variable, then the ideal point is this yellow dot. All the non-faulty samples are these blue points, and they are all samples from this unknown random variable. Byzantine outputs can be produced arbitrarily, and they have full strength in picking whatever point they want. And despite Byzantine points being added to our system, our goal is to still make a robust decision that is somewhere near this true unknown point. And so now that we've created this new assumption that points are stochastic, non-faulty points are stochastically distributed, we also need to define a new problem definition to solve this new problem that we've created. And so this new problem is called the stochastic Byzantine agreement problem, and it's comprised of a system R of processes where it's comprised of a subset Q of non-faulty replicas that are all samples from some random variable X. And there's also a subset of F Byzantine processes, and those outputs are produced arbitrarily. A solution to the SVA problem must satisfy three conditions. The first condition is a region agreement condition, and this states that every non-faulty process will produce an output, and that output will also be associated with a region guarantee. And the intersection of those region guarantees is guaranteed to include all the non-faulty outputs. And so what does this look like? So say we have a set of non-faulty outputs in blue. Each non-faulty output comes with a region guarantee. And the intersection of those region guarantees is going to include all the non-faulty outputs. The second property or condition is an accuracy condition. And this states that the true unknown point that we're trying to estimate will also be inside this intersection of the region guarantees. And so this ideal point has to be somewhere in this highlighted region. The third condition is termination. And this is a standard property that just states that all the non-faulty processes will eventually decide an output. So now that we've defined the stochastic Byzantine agreement problem, how does it compare to the problem solved by approximate agreements? So in stochastic Byzantine agreement, we have a region guarantee. But in approximate agreement, we have an epsilon agreement guarantee that states that in if the outputs of two non-faulty processes, in every point of their vector that they output, they will converge to be within epsilon of each other. So they'll converge to some pointwise distance of one another. In the region guarantee, this is not the case. So in the epsilon agreement, we have precise agreements, whereas everyone's converging to a single point. But in region agreement, this is a much weaker form of agreement. The difference here is that agreement for us is expressed in uncertainty regions, whereas epsilon agreement is in pointwise proximity. The second property of approximate agreement is a validity property that states that the decision will always be inside the non-faulty convex hole. And so what this provides is that this is a limited accuracy guarantee because it doesn't provide any guarantee on where that decision is relative to this true unknown point. Whereas the accuracy guarantee in stochastic Byzantine agreement is a stochastically sound accuracy property that ensures that the true point is always going to be within this region guarantee. The termination guarantees are relatively the same. It just states that all the non-faulty processes eventually make a decision. So now that we've defined a new problem, we also need to define a solution to this problem. And so the solution is called proximal Byzantine agreement. And the key idea behind this protocol is that our goal is to infer a robust estimate by treating all the replicated outputs as samples from an unknown distribution. And the way we're going to make point estimation is by using a robust stochastic estimator that maximizes the likelihood of our point estimation. We're also going to use a quorum selection mechanism that bounds Byzantine influence, and in contrast to approximate agreement or sensor fusion protocols, where you saw all the outputs were used to reach convergence, we're basing it on quorum selection, so a certain subset of the points will always be excluded in the point estimation process. The last thing is, in Byzantine vector consensus, we saw convergence, so iterative convergence over multiple rounds. In our protocol, there's no iterated coordination. So what is proximal Byzantine agreement? It's this equation here, and how you can read this equation is we have a set R of received outputs, and we also define the quorum size. So this is our quorum selection. How big is the quorum that we want to do the point estimation on? So that's S. So now the way this algorithm works is that we want to find an output X and quorum R pair that maximizes the conditional likelihood, the probability of X given R. So argmax just means that we want to find the output X quorum R pair that is the most conditionally likely. And how does this look visually? So say we have this probability distribution graph, and we have quorum Q1, Q2, and Q3. Our protocol will essentially determine the conditional likelihood of every single point in the output domain and determine its likelihood, and then we'll decide the point that's most conditionally likely. So in this case here, our protocol would return the output 5 given quorum 1, because it has the highest peak, it's most likely. Our protocol extends to multiple dimensions, not just a one-dimensional protocol. And the way we handle this in multiple dimensions is by overlaying a probability distribution over the output domain. One thing to point out here is I've also highlighted the non-faulty convex hole with the black outline. And in the non-faulty convex hole, every single point is valid point. So the protocol would satisfy all of its properties if we form a decision within this region. But in proximal Byzantine agreement, this lower region is actually a lower likelihood region. So we don't want to decide a point in this region. We actually want to pick one point. There's only one valid point given any received set of outputs, and we want to find that point that is most conditionally likely. The second benefit of our protocol is that we don't have a replica count dependency on dimensionality. And so specifically, we're required to have at least n greater than or equal to 4f plus 1 replicas, where the quorum size must be greater than 2f, and it'll be clear why it's greater than 2f in the next slide. So what this boils down to is we really just need more than s plus f, so the quorum size plus an additional f points to provide all the guarantees of our protocol. But one of the things to observe is that it's pretty expensive to compute the likelihood of every single point in the output domain, especially in continuous domains or how precise you want those computations to be. And so one way to optimize this is by making value selection based on the geometric median. And the geometric median is an algorithm that essentially finds a point that minimizes the sum of distances to the other points that are outputted. And one of the advantages of using the geometric median is that it's robust to just under half the samples being malicious. And so by having more than 2f points in your quorum size, it guarantees that you'll always have a simple majority of non-faulty points in the quorum, and thus your point estimation using the geometric median will then be resilient to Byzantine manipulation. So how does this look? So we have a set of points as we've had before, and let's say we also have a Byzantine point, and we also have this ideal point in yellow. So our protocol will iterate over all possible quorums, and we'll compute the geometric median of that quorum. We'll then assign a conditional likelihood value to it, and we'll do that for every single quorum. So we have quorum A, quorum B is 78%, and quorum C is 92%. And once we find the quorum that maximizes the likelihood, that's the decision that we end up making. So we only have a n choose s combinatorial cost here. So once we make this decided point in green, we also associate a region guarantee around this point. And this region guarantee is proportional to, one, the distance between the furthest point in the quorum to the geometric median, and it also has this extra constant factor that is based on the quorum size and the number of faulty points. And one way to view how this region guarantee can grow is that if we have higher variance non-faulty outputs, so non-faulty outputs that are generated from a random variable with higher variance, the points are going to be more dispersed, and as a result, the region guarantee will also be larger. But nevertheless, we still have the guarantees as I mentioned before. So one of the things that I built in my PhD is I built a web GUI that essentially allows you to visualize point estimation and compare it to other protocols. So this is a web GUI that I created, and you can just select some points. So basically we have a quorum size here of 3, and we have one faulty point, and we're kind of outputting here now. Yeah, so we're kind of outputting now the point estimation of Byzantine vector consensus and also the geometric median on all the points. So we have 4 points that are evenly distributed around the center 0, 0. And we can see that PBA has this quorum selection mechanism. So the decision that we make is this star, and we're basing this on these 3 points. Whereas Byzantine vector consensus and geometric median are all utilizing all the points on this graph. So their estimation is towards the middle. But as you can move points around, so we can create new quorums and view different point estimations and how that's affected. So we can have a point estimation over here. We see Byzantine vector consensus is here, so this is the convergence point for Byzantine vector consensus. And this is the geometric median here in green of all the points. And we can do this by adding more points and determining what the decision ends up being and what the point selection is. And one thing I'll point out is you can also change your quorum size. You can also trace the decisions that are happening. So if you want to enable how the geometric median is impacted, you can essentially pick one of the points, and then the geometric median will move around in your graph, and you can see what the skew of the geometric median is. And it also works for PBA and Byzantine vector consensus. So I'll stop here. Is there any questions on point selection before I move on?
Yeah, let me quickly ask. So actually, it's very interesting that you look into each one of the quorums, and if you can have a better estimate from any one of them, you pick that one. That's a very smart thing to do. But so the number you mentioned, the number is not going to be combinatorial. It should be, no?
Yeah, no, it is combinatorial. So the number of computations you have to make the point estimate, the point estimation with PBA is combinatorial.
Yeah. So then there is this cost, time cost.
Yes. So you have to do it. There's a factor on top of the geometric median.
And it's manageable?
So we'll show in the evaluations, we do a runtime and I'll present those.
Yes,
Okay. Okay. So now that I've presented proximal Byzantine agreement, well, what kind of applications does it apply to? And one of the things that we realize that it applies very well to is in streaming-based applications or applications that are interval-based, where you have a sensing, where a bunch of replicas produce sensing measurements, they make a decision, and then they produce another set of sensing measurements, and they make another decision, and they do this over and over and over again over time. So this applies to drone networks, autonomous vehicles, where they are measuring the distance between an object in every interval, and they need to make a maneuvering decision whether to brake, maneuver to the left, go to the right, reverse, etc. So there's a lot of applications that this applies to. And also these applications all have noise because they're all using sensors to make these measurements. So one of the things now that we're saying is if you're basing our applications on streaming, on interval-based streaming applications, we have to make some assumption on what the outputs of each interval are comprised of. And so our assumption here is that in every interval, the outputs are coming from the non-faulty outputs are samples from a locally stationary stochastic variable. And so what this means is that if we have n equals 4 plus 1 samples, then in interval t, there is a unknown random variable with an ideal point, that's the mean of this random variable. And all the non-faulty processes will produce point estimates from this unknown random variable. And then our goal is to make a point estimation given this scenario. And then in the next interval, t plus 1, we have a new random variable with a new ideal point. And we also have a new set of non-faulty points sampled from this new random variable. And again, our goal is to make a robust estimate. And in interval t plus 2, we have a new random variable, we have a new true point that we're trying to estimate, and we have a new set of samples from this a new set of non-faulty samples, and we're trying to make another robust estimate given these samples. And so one way to apply our protocol in practice is via the one-shot PBA protocol. And so how this protocol works is, say we have a sensor here on the left. This sensor is producing measurements that are being pulled by a set of replicas. And at output time t, each replica is continuously consuming these replica samples. They compute some function on the inputs that they received. And then they broadcast their function output to a consumer. And the consumer here is now getting a redundant set of observations from what the function output is. And then it uses PBA value selection to make a robust estimate. But now that we're in interval-based settings, we can also utilize stochastic modeling to track this interval-based assumption. So typically the interval from t to t plus 1 is correlated, and we can kind of track this object moving. So we can also utilize a local model to kind of capture and have more informative decisions based on the modeling technique. So once the consumer makes a point estimate, it updates this local parameter update, and then it waits for the next round of inputs from those replicas. One of the things to observe, however, is that we've kind of converted replicas to become data pipes. So in Byzantine vector consensus, all the replicas are going through iterative convergence until they reach agreement, and only once they reach agreement, they then output to the consumer, and then the consumer uses this point. Here, replicas are just data pipes. They consume a bunch of data, they compute a function independently of what everyone else's view of the input stream is, and then they broadcast that output to a consumer, and the consumer is running the agreement process and to make that robust decision. And so now that we've defined the protocol, what is the model of our one-shot protocol? So the first thing is that we assume, the thread model of this protocol is that we assume an omniscient adversary. This is the strongest kind of adversary. The adversary knows every single input across all the non-faulty processes, and it knows it in advance. It also knows every single output that each non-faulty process makes, and it also has unlimited time to compute its attack on the system. So it's the strongest kind of adversary that knows everything about our system. The network model is also applicable in different kinds of variations, and really the way we determine what network model to apply is based on the existence of having a 2f+1 quorum, non-faulty quorum. So as long as we can guarantee we received at least 2f+1 non-faulty outputs, we can always make a robust point estimation due to the geometric median being robust to having at least a simple majority of non-faulty points. So in the synchronous case, this means we need 3f+1 outputs because at time t, we are guaranteed to receive all the non-faulty points. And so if we receive at least 2f+1 points, we know we received all the non-faulty points. And if we receive 3f+1, then we know we received 2f+1 non-faulty points and f malicious points. So we can do our quorum selection mechanism in that way. In the asynchronous network, it's more tricky because we don't have a timing assumption of when points are being received, especially from the non-faulty processes. So we really need a minimum of s plus 2f points because there can always be f outputs that are withheld by Byzantine adversaries, and there could also be f points that are just delayed. So once we receive s plus f outputs, we're guaranteed to have a non-faulty quorum of size 2f+1 or of size s, and then we can always make a robust decision once this condition is satisfied. So really what this protocol is time invariant, and it's just dependent on receiving enough messages to make a robust decision. So one of the things that we're really interested in applying PBA is not just this consuming a set of inputs and then making a function and outputting it to a consumer, but in this iterative case where the consumers are the replicas that are consuming all the inputs. So in this drone network application, we have a set of drones, and they're all broadcasting to each other their leader locations estimate. And so each drone receives all the estimates or a subset of the estimates from the other drones. And then at interval t, once they receive enough points, they can compute PBA value selection on the points that they received. Then they can update their local model parameter based on the output domain that they're modeling. And then they can make their next maneuvering decision. And then they'll rebroadcast their leader location estimate again in the next interval. So at t+1, there's a new set of inputs coming from this drone network. Again, they'll run PBA. Again, they'll update their local model in an interval-based mechanism, and then they'll make a maneuvering decision and then broadcast another set of leader location estimates to each other in interval over and over and over again as the mission requires. So, but one of the things that is interesting is what's the fault model? How do we handle faults? So what if messages aren't all received across the network? So there could be scenarios where some of the messages to some of the processes are not received or dropped. And it can be in different combinations. So what does this cause our system? It just causes weaker agreements. And so each drone is only going to make a robust estimate once it receives enough inputs. But if each non-faulty drone is receiving a different subset of inputs, then it might make a different decision than the other ones. But that decision is always going to have the guarantee of region containment guarantee. The other thing that could happen is because everyone is operating on a different subset of inputs potentially, then the stochastic model that they're all maintaining may also diverge over time. So if we're updating based on what we receive. And so how do we resolve this divergence, or how can we have a form of proximal Byzantine agreement that doesn't just allow this weaker agreement, but also provides a guarantee on precision? And so we have this protocol called coordinated PBA. And this protocol works as follows. So we have a sensor or a set of outputs, and we have a set of replicas that are receiving these inputs. So at interval t, they basically use a multi-valued Byzantine agreement algorithm or protocol, and they all agree on the inputs that they received. This allows them for every interval, or for that one specific interval, to know all the inputs that every non-faulty process received. And then they all can, for each interval that they received of the inputs, they can do PBA value selection in a consistent manner. Then they can update the model locally in a consistent manner since they all received the same set of inputs. And then they can broadcast a new model to a consumer, so they have an updated model over time, or they can just utilize the PBA output that they all consistently agreed on and pass it to the consumer to make some controlled decision. So this is proximal Byzantine agreement, and now I'll talk about the evaluation, but if there's any questions, I'll pause here for questions.
So just on the last slide. So again, interesting that you can aggregate these into a model and evolve the model so you have more information for the next rounds.
Yeah.
So in classical Byzantine agreement protocols, there are these learners, right?
Yeah.
So I think you have similar things because you have a client that is supposed to learn from these replicas. Is that correct?
Yes.
And then you send the whole model to the learners every time. How large is the model?
So in our experiments, we've used we modeled distributions that had conjugate priors. So essentially what we could use is we basically have this update function that, given these set of inputs, how does this impact the mean of this random variable that we're managing locally, and how does it impact the variance? And we would model that over time.
So for
it's not
parametric distributions,
So-
it's just a few numbers.
A few numbers, yeah.
So I'll talk about this, or it's not in the slides, but one of the things is that we can, is an extension is using like machine learning models. The only challenge here is that is how do we utilize these machine learning models or I'll say it this way, in parametric distributions, we know exactly what the inputs and outputs are. In machine learning models, it's less predictive, and so how do we still have formal guarantees when we have these black box-esque kind of tools to use?
And is this client just a role, or you actually have external client? Because you have these drones, they're communicating. I think they are both learners and replicas at the same time.
So there's one thing that you can utilize is a hybrid model, where you have this fast path where you're doing one-shot PBA and you're making the most reactive decision possible. And then under the hood, and when it's most convenient, or every periodic period, you resynchronize on all the inputs you received and build a consistent model in a consistent way that you can rebroadcast to each other or to a specific consumer.
Yes, that's related to what I wanted to say next, that sometimes the last phase of this round can be merged with the first step of the next round, and you're safe if you don't have learners and replicas as separate processes. If they're the same process, then you can save. Can that be done here too?
Well, so if you have the drone network case, you could save, but multi-valid Byzantine agreement requires some coordination, so it requires additional messaging. But you could utilize a one-shot path where you make the reactive decision while at the same time eventually agreeing on or catching up from the past and having a short divergence window.
It also depends on you can consider applications that have multiple depths here of different processing in a data pipeline, and each of these is acting both as a consumer of incoming measurements and producing their own outgoing measurements, and so all of these are kind of overlapping. The multiple instances of agreement, for each phase of the data processing pipeline. And so these processes are both consumers and replicas, and they're kind of overlapping their messages for those protocols.
Yeah.
So how do we compare proximal Byzantine agreement to existing state of the art? And so I'll present 3 empirical evaluations that we ran. There are more evaluations can be found in the dissertation. So I have slides for them, so if we are curious, I can go over them as well. But I'll go over 3 just due to time constraints. So we compared against 4 other protocols, the geometric median on all the points, Byzantine vector consensus, which I explained earlier, Brooks-Iyengar, which I also showed the algorithm earlier, and component-wise median, which is essentially say you have a set of vectors, you do the median in each dimension independently, and that's your point-wise estimate. So on top of these evaluations, we also simulated strong attacks that we could figure out for these protocols. And again, due to time constraints, I have slides for the other algorithms, but I'll only present proximal Byzantine agreement. But if it comes up, I can show you the other ones that we simulated as well. So the attack model for proximal Byzantine agreement is the following. So say we have a set of 4 points, A, B, C, and D. Then our quorum size here is S equals 4, so we have 4 non-faulty points. So we ideally, one evaluation shows it's always best to have the largest quorum size possible. So we'll use quorum size 4. And the way we do this is we compute the geometric median of this non-faulty quorum and then associate a likelihood to that quorum. And so the likelihood here is Y. So now an attack is the attack model that we've defined is a colluding replacement attack via random sampling. And so the way we do this is say this is the true point. Our goal is to find a new point, say point F here on this graph, that pushes the geometric median further away from this true point, but also that the conditional likelihood of this new geometric median point given this new quorum is greater than the likelihood of the non-faulty quorum with that respective geometric median. And so the way we do this is we randomly sample points towards a cluster of non-faulty points, and we try to find the geometric median that pushes it the furthest away. So on top of that, our evaluations also contain 2 kinds of random sampling. The first kind is via symmetric distribution, where the mean is the center, so the ideal point is in the center of this random variable, and the non-faulty outputs are symmetrically distributed around this around the mean. The second kind of sampling was the asymmetric distribution, where the mean is in the center here again, but the non-faulty points are skewed more to the left than they are to the right, so we have an asymmetrically distributed points. And so the first result I'll present is accuracy by dimension. And so this result is showing a no attack scenario where n is increasing by dimension. So dimension is on the x-axis here and median error is on the left. So we want to be on the lower side of this graph. So being on the bottom is better. So what we're showing here is that at dimension 10, there are 13 total points that are being used for point estimation, whereas in dimension 2, there's only 5 points being used. So one of the results basically show that more samples leads to higher accuracy. So having more points to make a point estimation from is better. In the asymmetric case, under the no attack model as well, we see that the symmetry assumption of interval-based sensor fusion is already kind of being constrained. And one of the reasons is that a lot of the points are symmetrically distributed, but they may have larger intervals. So this causes the sensor fusion protocols that have the symmetry assumption to have increasing error as dimensionality increases, and this is especially propagated as we have more non-faulty samples. So in the attack simulation, we see something very different. In this case, I'm showing you the attacks for f equals 2. So we have 2 faulty processes, and here in dimension 10, we have d plus 2, so that's 12 times 2, which is 24, so we have 25 total points at dimension 10, and we have 9 points for dimension 2. So one of the things that we see here is increasing the ratio of non-faulty to faulty replicas still improves accuracy. So in dimension 10, we had, I think it was 25 total points, only 2 of them were faulty. In dimension 2, we had, I think it was 9 total points, and 2 of them are faulty. So we have a higher ratio of non-faulty points as dimensionality increases. And so we can see that accuracy still improves as we increase the number of samples. But one thing that is notable is that quorum selection seems to improve accuracy quite strongly. And so we can see here that the PBA result has the lowest error presented. One of the things you might be asking is, what is this PBA uniform graph? And so the PBA uniform is essentially, well, how we compute PBA is we assign independent likelihoods to each point that we receive, and we use these points to compute the conditional likelihood via a similarity-based approach. And so in the PBA normal case, we use a Gaussian distribution, so all the points have a different independent likelihood. But in the PBA uniform case, all the points have the same likelihood. And so we can see here that PBA uniform has higher accuracy than the PBA Gaussian case. And one of the reasons why this is happening is because the attacker is able to slightly manipulate how this point estimations and to improve its attack on our system. And so by not using this slightly modified distribution, it is maybe more robust than using a distribution that exactly tracks this output domain. And the results were also similar for asymmetric case, so I'm only showing the symmetric case from now on. But when we constrain the number of replicas, so now instead of increasing the number of replicas over as we increase dimensionality, we now say we have exactly n equals 4f plus 1 samples across all dimensionality. So we have 9 total samples at dimension 10, and we have 9 total samples for dimension 2. So the first thing to note is that Byzantine vector consensus cannot participate in this kind of evaluation. And the main reason is because its replica count to provide all of its convergence guarantees is dependent on the dimensionality. So it needs d plus 2 times f plus 1 total points. Whereas here we're only using 4f plus 1. So what our results show in this no attack case is that PBA is actually disadvantaged when there's no attacks. And the main reason is because we're utilizing fewer samples, so 2 fewer samples than the other agreement protocols or estimation protocols are using to make their point estimate. So we're disadvantaged by using less. But in the attack scenario, where we simulated the attack again with f equals 2, we see that quorum selection actually again does better and has better accuracy. And one of the things we can say here is that probability maximization, where we're not viewing a region as all valid, but picking the most likely point is the most valid decision, is a good point estimation technique. And again, we also had similar results for the asymmetric evaluation. I can show figures if people are interested as well. So the next thing comes to your point, what is the cost? And so we did this evaluation on 2 different kinds of chips. So the first one was an Intel CPU chip. It was, I think, $400 or $500 chip. And the second evaluation was on a Raspberry Pi 2W. So this is a very small edge device, and it costs about $20. So what we can see off the bat is that there's about an order of magnitude, so 10x cost by using a $20 Raspberry Pi chip in performance across all the protocols versus using a Intel CPU. The second thing that we can observe is that Byzantine vector consensus is at the top of the graph. It's the most expensive across all the runs. And the reason this is because Byzantine vector consensus uses an algorithm called finding the Tverberg point using Tverberg partitions. And this algorithm is actually quite expensive to compute, especially as dimensionality increases. In the middle of the graph, we have proximal Byzantine agreement. And proximal Byzantine agreement has about an order of magnitude better performance than Byzantine vector consensus in high dimension. And but the geometric median and all the non-faulty points is actually an order of magnitude more performant than proximal Byzantine agreement, which is also using the geometric median technique. And again, this is because quorum selection is combinatorial. So we do the geometric median, but we have to compute it and choose s times, whereas geometric median just computes the geometric median once. So now this introduces why would we want to use proximal Byzantine agreement, and why not just use geometric median, as it had very good accuracy as well. And the reason is that this introduces 2 different kinds of applications. So in some applications, you might prioritize only having reactive decisions. And in that case, you might prefer using the geometric median. But in safety critical applications where you might require some formal guarantees on the decision you end up making, you have to use proximal Byzantine agreement to be able to quantify your uncertainty and have a region guarantee around your point estimation. So there's this cost of having formality guarantees and having just a strong point estimate with no formality of where that true point may lie. So that's the big cost comparison that a system designer must make. But in any case, there are 2 valid and good approaches. So the final evaluation I'll demonstrate is a drone simulator evaluation. And so as you're seeing on this graph, this is a simulator tool that I generated. And essentially what we have here in blue is we have a set of follower drones, and we have this green dot is the leader drone. So in every interval, the non-faulty, all the drones are exchanging and broadcasting their leader location estimates. And then they're taking a redundant view of these leader location estimates where we added noise to those estimates. and then they're computing a point estimate and then maneuvering towards that drone. And they do this over in multiple intervals. And so the types of data that we used, we had 6 total processes, 6 total drones, and we also utilized 3-dimension vectors. So we were using the latitude, longitude, and altitude. So how does our protocol compare? So what we see here is we see that the drone simulated attack, we see that PBA is kind of in the middle, or it's the second from the bottom. And so, but notably, it has better accuracy than Byzantine vector consensus, which is the primary target that we were trying to beat. And one of the reasons is that the median had slightly better accuracy is in the specific case where we have an even number of drones, the median gets an extra averaging step, because when you have an even number of drones, you get to the middle 2, and then they do an averaging again. But if you had an odd, then you had to utilize one of the middle points in your decision. So there was more flexibility in the Byzantine attack in that scenario when there's an odd number of points than in an even number of points. So now we'll transition. Before I guess I go into the future work, are there any questions on the evaluation? Okay, so what is the future work of our protocol, or of this research? And so the first one is obvious. It's how can we tighten the displacement characterization or the region guarantee around these points? So as I showed earlier, it's basically the maximum displacement is the furthest point in the quorum to the center times a constant, which is based on S and F. But as the quorum size and the number of faulty components increase, then this region guarantee is also going to start increasing proportionally as well. And so one thing that would be really important is there a way to either remove this, to try to minimize this constant 2C, or find a new way to provide this region containment guarantee? One such way could be through a quantile function or some stochastic function to do this. The second future work amongst many, so see the dissertation for more future work, is optimizing quorum selection. So as I showed earlier, we have this combinatorial and choose S cost. Can we minimize the number of quorums to use to make a point estimation in? One metric that could be beneficial is the Cook's distance, where given a set of inputs, it basically associates some value on how much influence that point has to the random variable that you're trying to estimate. So maybe using that kind of function to minimize or reduce some of the points that you need to consider. But this will be very important if we want to increase the number of points in the system, and specifically in drone networks where you want to utilize hundreds of drones, and specifically you want to tolerate more than just F=1 malicious points, but have a higher F tolerance. So where do I see this research kind of applying in the next generation of applications? So what we're seeing here, decision making is moving from humans to autonomous agents. And the sensor inputs that autonomous agents are going to be utilizing will become the attack surface. So before we had humans and they could see these inputs and say, does this make sense, before they make a maneuvering or control decision. But now agents are going to be utilizing protocols, and so we're going to need to have mechanisms to defend the inputs that these agents are utilizing. And they're going to need to use redundancy and some sort of fault tolerance mechanism to fuse these sensor inputs and make robust decisions with formal guarantees, especially when some of those inputs can be from faulty adversaries. The final thing of this talk is what's coming next. So Owen and I are submitting parts of the dissertation to a journal, Talks. We're also planning on using some of the background work that I did for the dissertation as a survey paper that kind of talks about this tension and conflict between precision and accuracy. And the last thing is we are also considering doing a short workshop paper that is presenting this drone simulator and hopefully having more people be able to use it and compare different protocols with ours as well. So thank you very much, and I appreciate you all for joining.
Thank you, Roy. This is excellent. Thank you.
Did you intentionally choose Peter's old neighborhood for the drone simulation?
Yeah,
he said that, like, oh, that's my neighborhood.
Look up. Yeah. So, are there any questions?
This is great. Great talk.
Thank you.
Yeah, I also thought that it was a very good talk. The slides and the flow was excellent.
Thank you.
And as long as we're piling on praise, the dissertation is in great shape. I was blown away by the background. I got new perspective on like the Ben-Or algorithm. It's just one of the best background sections I've ever read in a dissertation. So just keeping on the praise.
Thanks, Peter.
It was hard-won background information that we had to
Yeah.
wade through.
Yeah.
There's a lot of relevant background, right?
Yeah,
there is.
But
It's spread across a lot of different sub-areas, which is
Yeah.
was an incremental discovery for us.
Yeah. And I don't know, and
Yeah.
I actually included in the latest draft the acknowledgement section, but I also want to acknowledge Peter. In my advancement, he was he helped us figure out what the direction to push this work in, and his direct feedback allowed us to get more appreciation from reviewers. And immediately after, we actually got 2 papers in, two back-to-back submissions in. So thank you very much, Peter.
Yeah, you bet.
So, are there any general audience questions before we close it and ask the hard questions to Roy? Yeah. Okay. Well, then, if we could excuse the audience, please.